Welcome to video 12 on the TTB course. This video is from part 3 of the course. In part 3, we consider techniques for modeling TT systems. In this video, we consider the modeling of platforms based on a shared clock scheduler. The material in this video is based on Chapter 12 in the ERES2 book. If you haven't read Chapter 12, I suggest you stop the video, read the chapter, and then come back and watch the video again. So let's begin at the beginning. The task sequences on processors in a shared clock design can be modelled using the techniques presented in video 11. However, there are some aspects of the design that we need to consider if we are to generate a more complete model. We need to consider the slave delay, we need to consider the slave jitter, and we need to consider the response times of the platform when the inputs are provided to one processor and the outputs are generated by a different processor. We're going to consider all of these matters in the present video. In the video, we'll be concerned with both local designs and distributed designs. The figure on this slide shows a local design, of course. So let's consider slave delay and slave jitter. You'll find full definitions of these terms in the ERES book in Appendix 1. We will have a delay between the tick generation on the master and slaves in platforms based on a shared clock scheduler. This slave delay is inevitable because it takes a finite amount of time to transmit the tick messages between the processors. The communication links between the master and slave may also introduce what we know as slave jitter. As always, you'll find full definitions of the terms that are in small caps on this slide, such as slave delay and slave jitter, in Appendix 1. So let's look at slave delay again. Suppose we've got two processors like this and they're running these sets of tasks. So microcontroller A is a master node, microcontroller B is a slave node in a shared clock network. So MCU A runs the A tasks, MCU B runs the B tasks. There's a delay, the slave delay, between the start of the tick sequence on MCU B compared with the start of the tick sequence on MCU A. And this delay arises through the time taken to transmit the tick messages between MCU A and MCU B. Of course, the length of this delay will depend on a number of factors, such as the communication protocol that's used and the baud rate or bit rate of this communication protocol. The slower the bit rate, the longer the delay in the transfer of these messages, the larger the slave delay. Slave jitter arises through a similar source. So slave jitter refers to the variation in the timing of the ticks on the slave relative to the timing of the ticks on the master in such a design. So this might arise, for example, if there was any variation in the transmission times of messages between MCU A and MCU B. As we touched on previously when we first looked at shared clock schedulers, we'd usually expect a shared clock scheduler to be run on a network in which there was no other traffic. So we have a complete TDMA protocol. The consequence of that would be we would expect the network to be clear when we send a tick message. So we're not expecting jitter to arise because of message contention, because we're not expecting jitter to arise because we cannot send the tick messages because there's some other traffic on the bus. That would generally be an error situation in this type of design. Instead, the jitter is going to arise through any variations in the time it takes to transmit a message between MCU A and MCU B on an empty bus. We'll look at some of the mechanisms that underlie that shortly. So let's start by modelling a duplicator design. That's a local shared clock design with two nodes, and we'll assume in this model that the two nodes are hooked together using a UART-based communication link. As we've touched on in the previous video, UARTs are typically a good idea. UART-based communications between MCU A and MCU B in this type of design are typically considered to be a good thing, because use of a UART will allow us to detect problems, variations in the clock frequency on MCU A and MCU B in a duplicator design. So we're assuming we have a shared clock scheduler based on two processors linked together by means of a UART-based communication link. And in this design we want to calculate the slave delay. We will assume that MCU A is the master, MCU B is the slave. We'll assume that there are 10-byte tick messages sent from MCU A to MCU B, and we'll also assume that the tick messages are sent from the scheduler ISR in MCU A. This is illustrated in the code fragment below. So we're assuming that within MCU A we have a fairly standard scheduler. One addition made to this scheduler is that we send tick messages from the scheduler ISR in MCU A in this shared clock design. We're also going to assume that the arrival of the messages at MCU B is handled via a DMA channel, with the result that an interrupt is triggered when a complete message has been received by the slave. We'll also assume the messages are sent with individual bytes packaged with one start bit, one stop bit, and 8 data bits. That is, 10 bits per byte will be sent. Given these assumptions, the question we're trying to answer is how long is the delay between the generation of the scheduler interrupt on the master and the generation of the scheduler interrupt on the slave. That is, what is the slave delay between MCU A and MCU B. The calculation is very simple. In this case, the slave delay in seconds is given by 10 bits per byte multiplied by the message length in bytes divided by the baud rate in bits per second. If we run the UART comms at 1 megabaud, then our slave delay will be 10 bits per byte times 10, which is the message length in bytes, divided by 1 million, which is the baud rate. And this becomes 100 microseconds. On top of this figure, we may also need to consider the overheads involved in the schedulers at both ends of the links. We would expect to have to make measurements on the hardware to obtain this information. However, it's likely that the contribution of the overheads on the schedulers to this delay value would be very small in comparison with the message transmission times. And in many cases we can probably ignore this. It's likely to be a fraction of a microsecond. In this type of design, we may also need to consider the slave jitter. In the case of a UART-based design, transmission jitter may arise from the fact that the clock for the baud rate generator in MCU A is not necessarily synchronized to the tick source. We can usually model such transmission jitter adequately as follows. Transmit jitter in seconds equals 1 over the baud rate. When the message is received, there will also be jitter introduced into the signal. In most cases, the UART will sample the incoming waveform from MCU A 16 times or 32 times the baud rate. You'll find this information on the MCU datasheet for the MCU that you're using. If the factor is 16 times, the jitter will then be given by the following. Receive jitter in seconds is equal to the transmit jitter divided by 16. It's obvious how to convert this if we have a 32-fold oversampling. In total, therefore, in this example, we have slave jitter equals 1 over the baud rate times 17 over 16. For example, at 9600 baud, the slave jitter will be approximately a little over 100 microseconds. At 1 megabaud, the slave jitter will be approximately 1 microsecond. Let's now consider a CAN-based design. Again, we'll look at a duplicator design, and the techniques can be extended quite happily to work with distributed examples. So let's look at a CAN-based design. Again, we want to calculate the slave delay. So we've seen this table before. We'll assume we have 154 bits per message in our CAN messages. That is assuming here 8-byte messages are being transferred. So 64 bits of data are being transferred, and that we have 29-bit identifiers that we're using. So you can adapt this as required if your data setup is different. So we're assuming 29-bit identifiers and 8-byte messages are being transmitted. So we've got 154 bits of data to transfer in each message. At the maximum CAN baud rate, 1 megabaud, the message delay will be up to 154 microseconds. As in the UART example, we may also have some overheads to take care of when the messages are sent and received, and these would need to be measured to make sure that they weren't significant. As we also noted in the UART case, it's likely that the message transmission delays will greatly outweigh any local delays that result from preparing to transmit or preparing to receive or receiving and processing these messages. So we've got a delay of around 150 microseconds here. What about the slave jitter in a CAN-based design? This is a little bit more interesting. So CAN uses NRZ coding, non-return to zero coding, in order to synchronize at a low level the transmission and reception behavior to make sure that you can transfer the data without difficulties and synchronizing the clocks at a low level in the CAN hardware. So rather than transmitting data that has a long string of zeros or ones, CAN will introduce additional bits into the message if you've sent more than 5 consecutive zeros or ones. An additional bit will be inserted into the message so that there is a transition that can be used for clock synchronization at a low level to avoid clock drift and misinterpretation of the data that's transferred. So in the example at the bottom of the screen, our original frame is shown, and our frame is shown with the additional stuff bits added into the message. It's clear what's going to happen here in terms of slave jitter. So, bit stuffing causes the CAN frames to become of variable length. For example, if we have 8 data bytes used and standard CAN identifiers, the minimum message length is 111 bits, the maximum message length is 135 bits, so we have a possible variation in message length of 24 microseconds at 1 megabaud. That's a significant level of jitter that we have in this design. So it causes slave jitter. Paper below by Nahas et al. Gives some suggestions about ways in which we may be able to reduce this jitter. The basic approach outlined in that paper involves software bit stuffing. So we pre-process the data to apply a known level of bit stuffing to the data frames before we pass the data to the CAN hardware. By introducing a known level of bit stuffing, we can compensate for this when the message is received, and in doing the transmissions in this way, we can significantly reduce the level of bit stuffing that we see in the messages. So let's now consider how we model response times. We'll consider a slightly more interesting example. So here we have an emergency response system that involves 3 microcontrollers. The system is intended to provide emergency shutdown behavior. When switch 1 is pressed, switch 2 and switch 3 should both open, resulting in a loss of power to, and we assume, a safe shutdown of the control system. As long as either S2 or S3 is opened in response to the pressing of S1, then the control system will be shut down. So we have some redundancy in the outputs. And what we're doing here is we are increasing confidence in the processing of the received messages by double checking them on the 2 microcontrollers. So we have a single communication link that runs from MCU-I to MCU-A. What we do is that when messages are received by MCU-A, MCU-A doesn't take action immediately. Instead, MCU-A checks that it's happy the messages are correct. It then, if it's happy with the messages, it sends a copy of the message to MCU-B. MCU-B checks the message, sends back a message, an acknowledgement message that says it's happy with the message, assuming it is. If only at this point, only if MCU-B receives a message that MCU-A has checked and MCU-B is happy with the message, then MCU-B will react. And only if both are in agreement will action be taken. So that's our basic setup here, and what we want to know is how long does it take between pressing this switch and beginning to shut down the power in our control system. So MCU-I is responsible for reading and checking the emergency stop input. If S1 is pressed, a message will be sent to the UART-based communication bus, sent on the UART-based communication bus to MCU-A. We will further assume that this is a GALS design. This means that the schedulers on MCU-I and MCU-A are not synchronized. MCU-A and MCU-B are involved in various activities related to monitoring the control system, and one of these activities involves monitoring the emergency stop input. MCU-A and MCU-B implicate a duplicator platform, as we've discussed previously, and you'll find detailed in the ERAS-2 book in Appendix 3. So this platform is based itself on a shared clock scheduler. So we want to model the response time of the system. That is, we want to determine what the interval will be between the pressing of S1 and the opening of S2 and S3. We can split this model into 3 consecutive stages. The time taken to detect the switch press on MCU-I and then send the message, the time taken to transmit the message, the time taken to respond to the message by MCU-A, MCU-B. We will assume there are 2 tasks running on MCU-I. I1 will check the switch, sets a flag based on the switch state. I2 will read the above flag and send a message with the switch status. We'll assume that switch debouncing is not required, but you could include switch debouncing in this example very easily if you wished, using the techniques that we've discussed in previous video. So that's how we're operating on MCU-I. So using the techniques that we've worked with previously, we can say that the time taken to start sending the message is period I1 plus the worst case execution time of I1 plus the worst case execution time of I2. We'll assume that a single byte message is sent, which is hex A5 if the switch is pressed and hex 5A if the switch is not pressed. The message is assumed to be periodic. We're not going to require a sequence number. There are going to be two possible message values, so we're not going to require a CRC check. We'll simply need to check that the message contents match one of the two permitted values every time the message is received. So let's now consider MCU-A and MCU-B. On MCU-A, we have two tasks, A1 and A2. On MCU-B, we have just one task running, B1. Task A1 is designed to check the data from MCU-I. It prepares to copy the data from MCU-I to MCU-B in the next tick message. Task A2 is designed to open S2 if MCU-I has requested this or if MCU-B reported a problem in the latest acknowledgement message. Task B1 is designed to check the integrity of the MCU data received in the tick message via MCU-A. This task will also open switch 3 if MCU-I has requested this and the message integrity is confirmed. So this task will finally prepare to inform MCU-A of any problems in the next acknowledgement message. So the system will then operate as follows. A message will be sent from MCU-I that says open switches. We assume that the message reaches MCU-A in tick interval T0 at time x1, which is shown in the figure, just after A1 has started. We will have processed this message in tick interval T1 by time x2. We will forward the message contents in the next tick message in tick 2 at time x3. This message will be processed by task B1 by time y1. We assume that the message status is OK and a switch opening is required. MCU-B therefore begins to open switch 3, also by time y1. We assume that S3 fails to open. We'll also assume that we'll be able to detect this failure, but will not attempt to do so immediately. So we'll try to open S3, we'll assume that S3 is stuck, closed, and that we're unable to open that switch. In this design, we're assuming that MCU-B reports back the health of the message OK, message not OK, in its next acknowledgement message at time y2. We assume that the message is OK. We're also assuming that until MCU-A has received confirmation from MCU-B that the message is OK, it won't react to the command in the message. So we're assuming here that the message is OK. This acknowledgement message comes back to MCU-A in tick interval T3, and we then begin to open switch 2 by time x4. Given this system operation, and you could choose different system operations, but this is the system operation that we're assuming here, the worst case time taken to respond to the message requiring that the switch be opened is therefore determined by the time that S2 opens in this system. And in this case, this is given by 3 times the tick interval on MCU-A, MCU-B, plus the worst case execution time of A1, plus the worst case execution time of A2. As long as one of the switches operates correctly, our model will be accurate. And again, we should note you can change the detailed operation of this. You may feel there are different ways in which you would wish to respond to the commands from MCUI. That's fine. Whatever different implementation you choose, you can, with knowledge of the task operation, model precisely how this system will operate. That brings us to the end of this video. Please read Chapter 13 in the ERES2 book before you watch the next video. Thank you for watching.